All right, so what I'd like to do today is, you have a homework assignment due. I want to just do a few more examples that are pertinent to the homework, and then we'll take questions on the homework in a few minutes, all right? So at the end of class last time, we had just learned this 2's complement rule, how to calculate the bit pattern for a signed integer in binary. So I'd like to let's do a few more examples, and then we'll do some examples with addition, and then we'll take questions about the homework. Now, let's suppose we have a 4-bit cell. Let's suppose we have a 4-bit cell. Now, if you have a 4-bit cell, that means that there is, it's going to look like this. This bit right here will be the sign bit, and the rest of this is the magnitude. Okay, are you with me? So 4 bits. So let's just do a few little computations on how signed integers would be stored. How would you store -1? So here's an example. How is -1 stored? And so here's what we do. What we do is we know it's a 4-bit cell, so we write down the number 1. The way the number 1 would be stored. Now, how would the number +1 be stored?
0, 0, 0, 1.
+1 is 0, 0, 0, 1. Is everybody clear on that? And now, so how do you store -1? You take the 2's complement of this. And how do you take the 2's complement of this? What you do is you flip all of these bits, like it says here. It's 1 plus not x. So if this is the number 1, then what is not this? 1, 1, 1, 0. And then what do? You add 1. So then what do we have? 1, 1, 1, 1. So this is how -1 is stored. That's the bit pattern for -1. Now, is everybody clear on that? Are we good? Now let's do another number. Let's do -6. How is -6 stored? Okay. So, well, how is 6 stored? I think it's 0, 1, 1, 0, isn't it? Because this is the 2's place and this is the 4's place. 2 plus 4 is 6. So this is how 6 is stored. Is everybody clear? So then how is -6 stored? So this is +6. Plus this is +6. So how is -6 stored? What do? 1, 0, 0, 1, and then, because you just flip these, and then you do what? Add what? Add 1. So what's 1 plus 1? 0, carry the what? 1. 1. What is this? 0, 1. Now notice here that up here, the way -1 is stored, which bit is this bit, this first bit? It's the what bit? And it is 1, as it should be. Are you with me? And you notice, what is this bit? This is the what? The sign bit. So it is 1, as it should be. On this next figure, you see, if you do the same thing with -2 and -3 and -4 and -5 and -6 and -7, what do we get for -6? 1, 0, 0, 1, 0, 1, 0. Do you see the pattern there? Are you with me? You see the pattern? Now tell me, with a 4-bit cell, here, with this 4-bit cell, what is the largest positive number we can store? The largest positive number we can store is in binary. What is the largest positive? So in binary, what is the largest positive in a 4-bit cell? No, it's not 1, 1, 1, 1. Because if it were 1, 1, 1, 1, there would be a 1 in the sign bit, and it would be a negative number. In fact, it would be what? We just calculated it. No, what is 1, 1, 1, 1? It's -1. So that's not the largest positive. So what's the largest positive?
0,
Yeah. 0, 1, 1, 1. Binary, which is what? 7 decimals. So that's the largest. Does everybody see? That's the largest positive. Yeah.
Why couldn't you do 1, 0, 0?
Because if you do 1, 0, 0, 0, and in fact, what is? Yeah. Because there's a 1, there would be a 1 in the sign bit. And this would be a negative number. I'm asking what's the largest positive. All right? But now look at this table in figure 3.9. The largest positive is 0, 1, 1, 1. Right? So, and that's 7. But look, let's calculate that bit pattern for negative 7. If this is the way 7 is stored, how is negative 7 stored? What would you do? You would flip these, right? So this would be what? 1, 0, 0, 0, and then do what? Add 1, and this is 1, 0, 0, 1. And sure enough, that's how negative 7 is stored. But do you see there's one bit pattern that we're not using? Actually, this gets back to what you pointed out a minute ago. There's one bit pattern that we're not using that is unused. Do you see? It's 1, 1, 1, 1, 1, 1, 1, 0, 1, 2, 3, 4, 5, 6. Do you see there's one more bit pattern that we're not using? 1, 0, 0, 0. And in fact, that is the way to store, what number do you suppose that would be according to this pattern, following the same pattern? Negative 8. So in fact, what happens is, in figure 3.10, these are all the values that you can store for a signed integer in a 4-bit cell. And what is the range in decimal from what to what? From what's the smallest? Negative 8 to what? To 7. So in 2's complement binary representation, there's always one more value on the negative end than there is on the positive end. Does everybody see that?
But it's still the same number of...
It's the same number of values. In fact, we saw that principle in chapter 1. How many values can you store with 8 bits? This is a 4-bit cell. How many values can you store with a 4-bit cell? 2 to the 4. So 16. And you count them up, there's 16 values there. But the values that you can store are from negative 8 to 7. All right? And guess what, you guys? If it were like a 10-bit cell, how would negative 1 be stored? All ones. And how would 0 be stored? All zeros. All right, and it would be from negative 1 more. Does everybody see it? Now, does everybody see the pattern? All right? Are we good? Now, there's one more thing. There's one more interesting thing about if you are given a binary sequence, and for example, in figure 3.11, we have a binary sequence, and how big is our cell size here? How many bits in figure 3.11? There's 10 bits, all right? And suppose you're given these 10 bits, 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, and you wanted to know what number that was. Well, there's a long way to do it and a short way to do it. And I think for this one time, let's do it the long way, and then we'll show you the short way, and you'll see why. We know by inspecting the sign bit that the number must be what? Negative, because there's a 1 in the sign bit. So we know that's a negative number. So one way to figure out what the number is would be to negate it and then figure out what the positive number is, and then it would be the negative of that. Do you see what we're saying? So how would you, so what we're doing is figure 3.11. Let's negate. Now how do you negate? What do you do? What do you do? Flip them. And so if we flip them, what do we have? Is everybody with me on this? And then do what to this? Add 1. What's 1 plus 1? 0 carry the what? 1. 1 plus 0 is what? 1. And then this is all 1, 0, 0, 1, 0, 0, 0, 0. Is everybody clear on that? Now, what positive number is this? Well, what are the places? 2, this is 1, 2, 4, 8, 16, 32. 2, 4, 32, right? 2, 4, 32. Is that right?
Yes.
And now what is this?
38.
38. 38. Therefore, this original number must have been what? Negative 38. So what we conclude is 1, 1, 1101, 1010, binary is negative 38 decimal. Now, does everybody see how we did that? Yeah.
Was the point of doing that because there's so many ones, it was easier to do it that way?
Well, no. It's just to show this is just to show how, you're given a negative quantity. One way to do it, kind of like the straightforward way to do it, would be to convert it to the positive value, and we know the place values, right? But there's another clever way to do it without doing it this way. So this is a second technique. What you do is, instead of looking at the ones place in the original number, you look at the zeros place in the original number. So here's how this algorithm would work.
Oh, yeah.
You see the one, so you see the one in the sign bit, you know it's negative. So then what you do is you inspect it. Now, so where is there a 0 in our original string? 1, 1, 1, 1, 0, 1, 1, 0, 1, 0. In the ones place, the fours place, and the 32s place. Do you see that? So this would be 1 plus 4 plus 32. So all you have to do is this. 1 plus 4 plus 32, and now there's one more thing that you have to do. Tack on an extra 1. You see? So you just tack on one extra 1, and you add this up, and what do you get? 38. So that number must be negative 38. Do you see how that? So that's a shorter way to do that. And now let me just do a couple of examples of addition and some ands and ors, and then we'll take questions about the homework. All right, so let's say that we have a 6-bit cell, and let's do this addition. 0, 1, 0, 1, 1, 0, and 0, 0, 1, 1, 0, 0. 0, 0, 1, 1, 0, 0. And what we're doing is add. And every time we do an addition, we always have to specify what are in the N, Z, V, C bits. Those are the status bits. So N, and always do them in this order, please. N, Z, V, C. Okay? All right, let's do this. What is 0 plus 0? 0. What is 1 plus 0? 1. What is 1 plus 1? 0. Carry the what? 1. 1 plus 0 plus 1? 0. Carry the 1. 1 plus 1 plus 0? 0. Carry the 1. 1 plus 0 plus 0? 1. Carry what? 0. So does everybody see then that this carry then is 0? Are you with me? Because that's the regular carry out. So if these were unsigned numbers, this would be the correct sum of these two unsigned numbers. All right? But on the other hand, if you interpret these as signed numbers, what are we doing? We are adding a positive plus a positive, and we're getting a what?
Negative.
A negative. Therefore, the V bit has to be what? 1. Now that might have answered your question. And the N bit is always a copy of this, of the sign bit of the result. And so N is 1, because that says whether or not the result is negative. And what about the Z bit? The Z bit is set if if the result is what? All zeros. Are they all zeros, yes or no? No. Now, okay, so now question?
But does the computer defaults to reading it the way that the V bit was targeted?
Yeah, that's a really good question. The question is, what does the computer do? And this is always really tricky concept. What happens is, there is one adder in the central processing unit that adds integers. Do you see what I mean? That's a hardware unit. And it adds integers. And these NZVC bits, these are all bits in the CPU, in the central processing unit. And what we are describing here is what happens every time an addition takes place. So it's up to the software to determine whether we are adding signed numbers or unsigned numbers. Do you see? And the way the software can decide whether n overflow occurs is, well, if these are unsigned numbers, n overflow did not occur because c is 0. But if we interpret these as signed numbers, n overflow did occur because v is 1. So it's up to the software, after the addition takes place, to check the status bit.
Okay.
Now that's how, this is a really important concept. This is how the hardware works. And all hardware works like this. Yeah. Question?
So the NZCV bits are not considered a part of the bit cell?
That is a really good point. The point is the NZVC bits are not considered part of the cell that holds the values. And that is yes, emphatically yes. They are separate. They are in the CPU. That's in a separate spot in the CPU. And they are set every time you do an addition. That is a really good point. They're not part of, they're not, see, because if you said, oh, well, let's just have another part for that. Well, but then that's a finite. What about beyond that? What about beyond that? See, so anyway. Yeah.
Are there additions?
No, yeah, so the answer is, what about simultaneous additions? There is a set of status bits for each add unit.
Okay. Okay.
And if you have multiple addition units that can happen at the same time, then each addition unit has its own set of status bits.
Okay.
Yeah.
So for then v would be...
No, hold on. You say if you start with signed numbers. You don't start with signed numbers. You don't start with unsigned numbers because there are no data types in binary. That's an important point. You can't tell by looking at a set of bit values whether it should be interpreted as a signed value or an unsigned value or an instruction or a character, an ASCII character. There are no types in binary. So you can't say, you say, well, what if you start with a signed number? You don't start with a signed number. Only thing you start with in hardware at ISA 3 level is bits. They have no types. They are binary.
So you can't tell me...
You can't tell whether this should be interpreted as a signed number or an unsigned number. It's up to the software to test this afterwards as to whether the software wants to interpret this as a signed number or an unsigned number. This is a really, really good point. I'm glad you asked that question. You see, there are no types at ISA 3. The only type is binary. ISA 3, the language is binary. Bits, ones and zeros, that's it. And this is what happens in the hardware.
Okay.
That was a really good question. Ponder that. That was an excellent question. Yeah.
So like when it multiplies something by, let's say, a negative number, does it automatically set the...
Okay, yeah, a good question. So first you say multiply.
Yeah, I mean, does it add it, but before it adds it, automatically sets the sign bit?
Yeah, okay, multiplication is a different issue.
Okay.
And so the circuitry to do that is different. And in fact, that's beyond the scope of this course. Multiplication. Multiplication is beyond the scope of this course. I mean, hardware multiple. Well, no, actually, I take it back. You are actually going to write a program that multiplies. You will write a program that multiplies.
Can you just add it to it?
Well, no, there's an algorithm that does it, and you're going to write one. You're actually going to write one. But in hardware, I guess hardware multiplication is beyond the scope of this course. Software, you will do it.
Just because...
No, not empty. V is either 0 or 1.
It would just be, there's no place for v unless we're dealing with signed integers.
But all 4 of them are set with every addition.
Yeah.
The software can choose to ignore it.
Yeah. Okay.
Yeah. First in figure 3.12, back to this, if you have a 3-bit cell, then, and you are considering these 3-bit quantities to be unsigned numbers, then the values go from 000 to 111 in binary and from 0 to 7 in decimal. But now if you consider these to be signed numbers, then what would the range be, what would the positive range be? If they were signed, then the largest positive number would be what? 3. So what would the 111 be? That would be what? -1. So do you see then on this next part of the figure, it's like what you're doing when you consider them to be signed, it's like you breaking the number line in the middle and you're shifting it over to part B. See, so you have the same number of values, but it just wraps around, yeah. So that's one way of looking at it. It's another way of looking at it. And in fact, if you can do some conversions using this concept, and you can shortcut some of this binary twiddling by using this idea. So then here in figure 3.14 is a picture of the number line, these two number lines superimposed, 0, 1, 2, 3, 4, 5, 6, 7, superimposed over -4, -3, -2, -1, 0, 1, 2, 3. All right, but now, here in figure 3.15, this is a dramatic example of the fact that the default in C and C++ and Java and practically all high-order level 6 languages, the default is to do what? Is to not check the overflow bit. The default is to not check the overflow bit. So even though we are going to see how to do it in assembly language, in fact, you should be aware of this, that in C, the status bit is not checked. The program just keeps on running. Yeah.
But by not check the overflow bit, it still check, well, it already is trying to interpret it as a sign.
Right. And that's a good point. So in this program, notice in figure 3.15, we have an integer named n, and it is an int. So when you say int in C, that means a signed integer. Okay, that's automatic by the language. It's a signed integer. So that's what int means. All right. And what this program does, you can see what it does is it sets int. Oh, and by the way, I ran this on a computer that uses 32 bits to store the integer value. So tell me, what is the largest number that you can store in 32 bits in binary? What's the largest positive value that you can store with 32 bits in binary? 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 7, 8. Is that 32 bits?
Yes.
Guess what number this is in decimal?
2.
It's 21474836647. What's the one just before this? 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Ah, the one just before this one.
1,
0. And guess what the hardware did? It added 1 to this, and it got this. It added 1 to this, and when it added 1 to this, what's this? When it added 1 to this, what did it get? Got 1 plus 1 is 0, carry the 1, what? 0, carry the 1, 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 0, 0, carry the 1, 1.
So it's the negative up.
And that's where the negative 214784638 came from, because what's in the sign bit? The 1. And if you get to that point, that's literally what will happen. That's a printout. You can run this program, it'll do that. Well, if it's 32-bit integers.
You tried to add. Did you add precisely 1 to?
Exactly, precisely. There's the program. There's the code for the program.
Yeah. If you added, say, more than that, like in one go,
In one go, it would still wrap around and do that. It would wrap around and give you the negative value, the incorrect negative value. So it doesn't check by default.
So you just gotta be careful.
And I tell you guys, bugs, accidents have happened in software that was buggy because programmers didn't realize this.
So the VBit, is the signed overflow.
Yes.
Whatever.
Yes.
It is set to a 1
If there is a signed overflow.
but like defining signed overflow to be
That's a good-
the very last digit changed from what it previously was.
Okay, that's a very good question. So let me just give you the easiest way to determine whether V is set or not. If you add 2 positive quantities and you get a negative quantity, So if you add two quantities with a 0 in the sign bit, and you get a 1 in the sign bit, V is set to 1.
What if it was 2
If you
ones
add two,
and got a 0?
if you added if you add two negatives, and you get a 0 in the sign bit, that's also an overflow, because what happened is you had a negative number plus another negative number, you went outside the range.
So, but if it was
But
1 and 1 0?
if there's 1 1 and 1 0, it's impossible to get an overflow, because think about the number line. You're over here on the number line, and then you're going the other direction on the number line. You'll never be able to have an overflow. So there's never an overflow if you're adding two quantities of different signs.
Okay.
That's the rule that you should use. That's how you should determine it. Now, we will see, you guys, actually, if you take the computer organization class, we will actually construct the digital circuit for this adder, and you will see precisely how the V-bit gets implemented in hardware.
Is that the course where you get?
That's the course where you plug in those circuits. And computer organization, it's a great class. You should take it, plan on taking it if you want. All right. Now, the next thing is that these 1s and 0s, so we reviewed the status bits. The next thing about these 1s and 0s is that they can be interpreted as logic quantities, Boolean algebraic quantities. And so you guys from your logic class, you know and or and exclusive or. So in figure 3.16, these are the truth tables for how you combine two bit quantities with the AND operation, the OR operation, and the XOR is the exclusive OR operation. And then in figure 3.17 are the same tables, but this is how you think of them at level HOL6 as logic quantities. So basically if you compare part A of figure 3.17 with part A of figure 3.16, we see that a 0 in binary corresponds to what in logic?
False.
False. And 1 corresponds to true. Okay? So let's do a few logic ones. So suppose we do 0 1 1 0 1 0, 0 1 1 0 1 0, and 0 1 0 0 0 1, 0 1 0 0 0 1, and we AND these. So now what is false and true?
False.
It's false, so that's 0. So anytime we have a 0, false and anything is what? False. So anytime you have a 0, it's always what?
False.
0, yeah. So 0, 0, 0, 1, 0. Right? Now here's the thing. When you do logic operations, then you are not assuming anything about the whether it's a signed or an unsigned number. So in the hardware, the only bits that are set are N and Z. So here when we do this, we just have to say N equals and Z equals. Now, so what about N? Is N, is it negative, yes or no?
No.
No. And are they all zeros? No. So does everybody see how that works? Yeah,
I had a quick question.
sure.
Okay.
Yeah, now we're ready for homework questions.
Okay.
Yes, the output needs to be in the console.
Okay.
The same way that I set it up, because I'm going to test it on the command line.
Okay. Yeah. So.
Yeah.
Alright, so
Or sorry, it needs to be, leave the input, don't mess with the input or the output, the way it's set up.
Yeah, I just wanted
Yeah.
to make sure you didn't.
Okay, and I've already helped a couple of people with the how to run a Java program. Now, let me just take this chance right now to explain the what we're going to be doing in here with the homeworks. So in the book, a lot of these binary exercises are the problem says write a program in C, and what we're going to do in this course is, and I mentioned this once before, you are going to write a really big program, translation program in Java. So what I'm doing is I'm having you do these early exercises in Java so we can get used to using Java. So some of you may not have programmed in Java before, but it's very similar to C++. You should have no problem picking it up. But I want us to start programming in Java in preparation for that big project. So that's why we're doing them in Java instead of in C. Okay? So that one program that you wrote in C for the Towers of Hanoi, that'll be the only program you write in C. We'll just be studying C programs from here on out, but we won't be actually writing any more C programs. All right? And then what you should do, and let me caution that I link to a document that says how to hand in your homeworks in Java as a .jar file. So .jar, that's the standard Java archive file. And the thing about NetBeans is that your NetBeans might by default not include the source code. And so you need to go follow that link, and it'll show you how to use NetBeans to ensure that the source code is included in your .jar file so that we can have your source code to look at it, to grade it, to evaluate it.
I think the newest version, I think they fixed that.
You know, I was just helping somebody with that just a few minutes ago, and I think the newest version might by default leave the source code in.
Yeah.
So maybe so if you have an older version, that might apply to you, but yeah, I just discovered that just a few minutes ago. So anyway, that's a good deal. Okay, so now, I think this covers all the material that you need for the homework for tonight, right? And let me emphasize again that for the written homework, it needs to be typed and it needs to be handed in electronically, okay, as a PDF file. So make sure to export as PDF, don't just change the extension to .pdf. Are you with me? Yeah.
I thought last time you said we could write it.
No, that was for the last assignment. For this assignment, yeah, different assignment, different rule. Okay, are we good? Is there any more questions now about the homework, about any of this material? Yeah.
What's the C?
Carry. C for carry.
Okay, so how do you know what that?
You mean with this?
Well, not,
With and?
yeah, or just in general, I guess.
No. Well, okay, so here's the thing. If you do and, or XOR, C is not affected.
Oh.
It's only affected if you do addition, or arithmetic shift left, or arithmetic shift left. All right, so now a couple more concepts now. Figure 3.18. Okay, figure 3.18 is a little table that shows the symbols that are used in a language called register transfer language. Okay, and this is abbreviated RTL. So this is the language that specifies hardware. Now, in the industry, there is no single register transfer language that is universal. Every company has their own, provides a product that has their own RTL, register transfer language symbols. And so what I've done here for this text is I've just used the common ones, okay? This is kind of it's representative, but you should be aware that there's no one single standard, okay? But this is common. So let's just take a look at them. The AND operation, that looks familiar, right? The caret, that's like from logic, okay? It's like conjunction. OR is disjunction symbol. XOR, exclusive OR. Now the symbol for exclusive OR is a plus with a circle around it. Okay? Do you remember what that was in our logic class? Do you remember the symbol? We had a symbol for that one in logic. Do you remember what it was? In formal methods, do you remember in formal methods what it was?
For what?
For exclusive OR. It's 1 if they're different and 0 if they're the same. And so this symbol in formal methods, we wrote it like this, not equivalent. It's actually the same thing. But this is common in hardware notation. So I'm going with what is more common. And then not, that's our negation symbol. Implies, so we're used to implies. Now the transfer operator is a left arrow. And this left arrow, have you guys, some of you guys I think have programmed in R, right? The programming language R. So this is like the assignment operator. This is the hardware equivalent of the assignment operator, and it's the transfer. So it's when a cell gets information transferred into it, you indicate that with the left arrow. And then our bit index is going to be angle brackets. You know, in software, if you say B sub I, like this, it's square brackets, okay? But our bit index, it would be like this. It would be like B sub I, but it's the same idea.
This is just for like if we're writing it out.
This is a particular language called register transfer language that is used to describe hardware operations.
Is it ever used and like translated by any sort of?
Actually, the question is it ever used and translated? And the answer is yes. You can actually, nowadays what you can do is you can design a circuit by giving the RTL specification, and then a compiler will take that and will create the circuit for you. Yeah, it is cool. Yeah. So that's why it's an important concept. But it's the same translation principle that happens at a different lower level of abstraction. Yeah, I tell you, you guys, the computer systems, there's these ideas that with languages at each level and levels of abstraction that all...
It's a kind of carryover.
Yeah, it all carries over from one level to another, yeah. And then our informal descriptions are going to be in braces, and now there's two more. There's a sequential separator, which is the semicolon, and then there is a concurrent separator, which is the comma. So sequential means happens one after another. Comma means happens at the same time. Well, the comma in C++ is slightly different. Yeah, so that's not quite the same. But anyway, let me give you here the RTL specification of the OR operation. So you know, if we were to do this, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 1, 1, 1, 0, 0, and if we did OR, how would you OR? Now, how does the OR operation work?
If there's true, it's true.
If it's 1, it's always 1. The only time you have zeros is if they're what? Both zeros. So what would this be? 0, 1, 1, 1, 1, 1, 0. And what did we say the two bits were that were affected? N and Z, right? So what would they be?
Both of them are false.
Yeah, N it's not negative, and they're not all zeros. So now here's a specification of this. Well, the way this would work is this one is A, this one is B, this one is C. Do you see how does everybody see how that works? So what happens is C gets A or B. And what about N? What does it say N get? Oh, and by the way, semicolon, what does that mean? After that happens, after the OR operation happens, then what happens? N gets what? C is less than 0. Well, is this C less than 0? No, because it's positive, because of the sign bit. So that's how the N gets 0. Is everybody clear on this? And then what does it say Z gets? C equals 0. Well, is this C equal to 0? Is it all zeros? No, so Z gets this. And by the way, when do these things get set? How do these things get set? At the same time or one after the other? At the same time. So in the hardware, that happens literally concurrently. Now, does everybody see that? How that works? Now, does everybody understand how that is a specification of this? And what's sequential versus concurrent were. And here again, you guys, if you take the computer organization class, you will see at the microcode level stuff that's happening concurrently in the hardware and stuff that happens sequentially in the hardware versus sequential. All right, now here's a new operation called arithmetic shift left, ASL. Now actually, a good way to understand this is by analogy with decimal. What would happen if you had a number like 2,387? What would happen? Let's just suppose that you have a number 2,387 in decimal. And you shift left, you shift every digit over to the left, and you shift in a 0 from the right. Do you see what I'm saying? What number would you have? 2, 3, 8, 7, 0. That would be an arithmetic shift left in decimal, would it not? And what did you do to the number when you were, if you do arithmetic shift left in decimal? What do you do to the value of the number? You increase by how much?
By 10.
You multiply it by 10. Well, what do you suppose? Do you see that the arithmetic shift left operation, as shown in figure 3.19, shifts a 0 in on the left bit, and then the right bit goes into the C. So what do you suppose you're doing to the value of that number?
Multiply by 2.
You're multiplying it by 2. Are you with me? Here, let's do an example. So let's do ASL, let's do a 6-bit cell. And let's do this. Let's do ASL 111100, 111100. Now, oh, and by the way, what does the figure say C gets? The leading one, right? Okay, so now if we do an arithmetic shift left here, what happens? This one goes into the C bit, this one goes here, this one goes here, and so what do we have here? 1 1 1 0 0 1 0 0, and then the 0 that got shifted in, right? Did I write that down right? This is a 6-bit cell, right? This one goes out into the C bit. This went over here, this one over here, this one over here, so 0 0. Is everybody clear? Right. But now what about the status bits? What about N, Z, V, and C? So how about N, Z, V, and C? So in the end, it's negative, right? So that's 1. Are these all zeros? No. Was there an overflow? Now, how do you tell if there's an overflow? Well, we started with what kind of a number? A negative number. And what do we end up with? A negative number. So, no overflow. So V is 0. And what about C? C is 1 because this got shifted out into the C. Now, let's see if this, in fact, doubled the number. What is the original number? 111100. Oh, let's use our new, we can use our new algorithm. Do you remember how to figure out what number this is? No, that's the long way. What do we look at? So this is what? 1 plus 2 is 3. And then you have to add in the extra 1. So this is negative 4. Is everybody clear? Now, what about this number? What about 111000? Now what do we add? And this is binary, right? So now what is this? 1 plus 2 plus 4 plus an extra 1 is 7, and then plus an extra 1 is what? 8, so this number is what? Ha! It doubled. Is this stuff cool? Yeah?
So it always doubles no matter what?
Yeah, unless it overflows.
Yeah.
So here, let's do 010110. Here, let's do ASL 010110. 010110. So what is ASL of this? And then after we do that, it will do N, Z, V, C. So now, if we shift this left, what's it going to be? This one's going to go here, right? So it's going to be 101100. 101100. Is everybody clear on that? And now, what got in this? What happened to this 0? That went into what? That goes into the C. Right, by that figure. See the figure? Okay. And now, what about N? Is the result negative? Yes. Is it all zeros? No. Was there an overflow? This time there was an overflow because we tried to double a number, and instead of doubling it, we got a negative number. considered as a sign. So V is 1. Are you with me? And then you could figure out what these numbers are, and you could see that, anyway. Is everybody clear? So anyway, that's ASL. Another one is, the other one is shift, arithmetic shift is arithmetic shift right. If by shifting left you double the number, by shifting right you do what? Cut it in half. So can you ever have an overflow? No. And look at that sign bit. What happens to if you do an arithmetic shift right? What do you do with the sign bit? It's replicated. Do you see? So if you do an arithmetic shift right of a negative number, it always stays negative. You keep the sign bit the same. And in an arithmetic shift right, you always keep the sign bit the same.
But what if you were not trying to, what if you had an unsigned number and you did that to it?
Now that's a really good question. Yeah, if you do an unsigned number and you do this to it, remember, there are no types in binary. This is what ASR does.
So you're just not allowed.
And so, no, it's not that you're not allowed to do it. You can do whatever you want because there's no types. There's no type checking. But it would be meaningless. I mean, if you want to interpret that number as an unsigned number, then that's meaningless. That would be a meaningless operation.
Yeah.
Are you with me?
And so,
Wait, did I say that right? If you want to interpret that, if you want to interpret that number as an unsigned number, then the sign bit has no significance. And so that would be...
But it would screw up the number. If you tried to interpret both the pre-ASR number as an unsigned
well, it would be it would be meaningless. But there's nothing to prevent the hardware from doing that because there's no types. Which brings us back to that same point we were making earlier, with signed versus unsigned. It's the same kind of thing. I'm sorry, but it's time to go. So anyway, good deal. So there's a little more information about hexadecimal. I'll let you read about that, and we'll unfortunately have to cover some material on Monday that we need for our assignment on Monday. But we'll go ahead and forge ahead and do that anyway. Good deal. See you next time.
So